Good evening, everyone, and welcome back to day 3 of regulatory analytics. So today we'll be covering a very important point about in machine learning, and that is known as EDA and pre-processing. Now, EDA and pre-processing are the backbone of any ML project. Now, a lot of people tend to take EDA and pre-processing lightly, but we should not be making this mistake. EDA is a crucial part of understanding how our data is behaving, and pre-processing is used to clean up the data. Now, when we are working in a real-time project, the data that we would get, most of the times it will not be very user-friendly. There will be a lot of errors in that data. There will be a lot of flaws in that data. In order to overcome these flaws, we use pre-processing and EDA. Now, they go hand in hand. It's not like we do pre-processing first or EDA later, or EDA first, pre-processing later. They both go hand in hand. All right. So let's start. So what is EDA? EDA is known as exploratory data analysis. So what we do in EDA is we try to visualize our data. All right. This visualization of the data is very, very important. Without visualizing our data, we cannot really do anything with it. What happened here? So, all right. So let's understand it. So in EDA, we do a few very important things. The first thing we do is business moments. Now, what is meant by business moments? These business moments, they tell us about how our data is structured. So we try to take our data and we try to make some logical conclusions out of it. All right. So that is done under EDA. So let's take a look at the various forms of EDA. So in EDA, we also do something called descriptive statistics. These descriptive statistics refers to the 4-moment business decisions that we were talking about. So the first moment is all about central tendency. So here what we are trying to do is we are trying to find out how central our data is. All right, we are trying to look for how central our data is. In this, we calculate the mean, the median, as well as the mode of our data. So these 3 things we calculate. This gives us an idea on the centrality of our data, how the data is structured. Where is it structured? All right. And the second moment is all about the spread of the data. Okay. or we can say it is all about the dispersion of the data. So in this, we calculate the variance, the standard deviation, as well as the range of the data. Now we have a formula for variance. We calculate using that. For us, it is easy because we directly use Python. Within Python, we can calculate the variance. Now, standard deviation is nothing but the square root of the variance. All right. And then finally, we have the range, which is the maximum value minus the minimum value. Okay. So this is the second moment business decision. So the first two are fairly simple to understand, but the complications can sometimes happen while understanding the third and the fourth business moments. What is the third moment? The third moment is known as skewness. Skewness, it is also a measure of asymmetry. So we are trying to find out how asymmetric our data is. And in skewness, we come across the concept of long tail. So let's take a data and we'll plot it using some histograms. All right. So this is our histogram that we are looking at currently. Now, just give me one moment, please. Sorry about that. So this is our histogram. Now, let's see if we want to calculate the first moment. This will give us how central our data is. Around this portion, most likely will be our mean, median, and mode. Then we can calculate the second moment. Using all these data points, we can calculate the variance, the standard deviation, and using this point and this point, we can calculate the range. So this is our second business moment decision done. Now we come to third business moment. So what we try to do is we try to draw a line that covers our data. Now here, as we can see that it is moving up quite quickly. There is nothing here. This point is starting from here. There is nothing here. And it is moving towards the right. As it is moving towards the right, the line is tailing towards this side. This is known as long tail. Now this long tail is giving us the furthest point to the data. So this is a graph and this is our origin of the graph. When your data is tailing towards positive infinity, it is known as right skewed. All right. Similarly, if we draw another histogram here, and here the long tail is moving towards negative infinity, or it is moving towards the origin. This is known as left skewed. So this is telling us how asymmetrical our data is. And it can also help us potentially identify outliers. Now, what are outliers? It is something that we will cover later on in today's session. All right. So this is skewness. Similarly, if we have a data that looks like this, let's say, for example, this is a central point, and we have equivalent points on either side. The data is not tailing to the right or the left. This is known as no skewness. And when we have no skewness, we have a normal distribution. So a normal distribution is quite important for the next point. And the next point is known as ketosis. All right. So far we have covered the 3 business moment decisions, and the next one is we are covering is ketosis. So ketosis is only checked for normal distribution. Okay. So when we are doing ketosis, we are only checking for normal distribution. So let's take 2 examples here. Let's take this as a histogram. Right, and this is another histogram that we have. We have 2 histograms here, so we'll measure for both of them. So here again we draw the lines. All right, so here one thing we'll notice is it has wide peaks and thinner tails. There is not much tailing going around on either side. So this is known as negative kurtosis. All right, and then here we look at it. We have thin peaks and we have wider tails. This is known as positive kurtosis. All right, so these are the 2 scenarios that you might come across when you're doing ketosis. Now remember, ketosis can only be done on normal distribution. Okay, so now that we have covered 4 business moment decisions, let's see what is next ahead. what's next ahead is graphical representation. All right. So what is the meaning of graphical representation? It means visualizing the data in graphical manner. All right. So what is going on here? So our data would look something like this. You will have multiple columns and you will have multiple rows. These would be your headers. And let's say we have name, age, and some other column, gender. Okay, so these are the 4 columns we have. Now we are trying to do some analysis on these, where these rows represent your data. Okay, so what sort of analysis can be done here? First thing can be done is univariate analysis. What is the meaning of univariate analysis? It means one variable analysis. You're taking one variable at a time. So let's say, for example, we are taking the age column. If we do any sort of visualization where only the age column is taken, that is known as univariate analysis. Okay. And then let's say we also have bivariate analysis. In this, we are taking 2 variables. All right. An example before we move forward for univariate analysis is histogram. All right. In bivariate, we have something called a scatter plot. This is just a one example. All right. We have multiple analysis, multiple types of visualizations that can be done. But an example is scatter plot. So we can use this scatter plot to compare 2 analysis. All right. So let's say, for example, we are taking the age and the gender column. So here we would have gender, male and female. And here we would have various ranges of age. So the data would be spread like this, something like this. So this is a very basic example of a scatter plot. A scatter plot can also look like this. All right. Depending on what is your X variable and what is your Y variable. Okay. So this scatter plot becomes very important later on when we discuss linear regression, because scatter plot is going to give us an idea on how linear regression is going to work. All right. So this is scatter plot. Let's say we add another column to our table. This is known as job role. Okay, what sort of job role they're doing. And now we want to compare these 3. Okay, we want to compare whether these 3 columns are going to work together or not. So in this, we use something called a multivariate analysis. So this is 3 or more variables. So wherever you have 3 or more variables, use multivariate analysis. All right. So what happens in multivariate analysis? We use something called a pair plot. A pair plot is a combination of a scatter plot plus a histogram. Now this histogram can be changed for other univariate plots, but basically it is a combination of a bivariate plot and a univariate plot. So this is going to give us information of more than one column. And then we also have something called as the interactions plot. Interactions plot is a little more difficult to understand, but I'll try to give the gist of it. Basically, we have multiple variables. All right. Now, interaction plot is telling us how likely are those variables interacting with each other. So wherever they are interacting with each other, that is known as an interaction plot. All right. So we'll see how interaction plots work tomorrow. Okay. But normally these are very rarely seen, but they can be useful in specific scenarios. All right. So this is in regards to EDA. So far in EDA, we have seen first business moment decision, second moment business decision, third business moment decision, and fourth business moment decision. And then finally, we have seen 3 different kinds of graphical representations. We are looking at univariate analysis, where we are taking a single variable and we are trying to make some sort of analysis for that. Then we are taking bivariate analysis, where we are comparing 2 variables against each other to see the level of interaction between them. And then we are doing multivariate analysis, where we are taking 3 or more variables. All right. So this is known as EDA. So now that EDA is complete, let's jump over to pre-processing. Now, like I said, just like EDA, pre-processing this is the backbone. Pre-processing and EDA are the backbone of any good ML model. All right. So pre-processing involves cleaning up of the data. This cleaning up of the data is useful to, cleaning up of the data is useful because we are always in some manner dealing with some sort of messy data. All right. So let's see what all we do in pre-processing. In pre-processing, we have 10 different kinds of pre-processing techniques that we use. We use typecasting, we use typecasting to change the data type. Okay. Then we use So let's see what happens in typecasting. So let's say, for example, we have temperature. Temperature, let's say, is 25.8 degrees Celsius. All right, so this is known as float values. All right, so let's say our variable x is declared as 25.8, but we don't want it to be in float. We want it to be int. So we can make that change. So if we change it, this becomes 25. All right. And then it becomes an int. And then we want to rechange it to float. If we do that, this becomes 25.0. It is again float value, but it has lost the previous value that was stored. So this is one thing that we have to keep in mind when we are doing pre-processing. So what we'll do is I'll open up the code and we'll walk through pre-processing and we'll explain as we go through it. So just give me a second. I'll open it up. All right. So, okay, it is still not open. All right. So let's open up Spider. All right. So first thing we are taking a look at is in data pre-processing. So in data pre-processing, we are looking at typecasting. So in typecasting, we are taking the data type of one variable and we are converting it to another form. So we take the data, we load the data. Now here we can see the data types. All right. So object means some sort of string value. Int 64 means it is some sort of integer value. All right. And float 64 means it is a float value. Float values have a decimal point and int values don't have a decimal point. So what we'll do is we'll take this salaries, this column that is in float, and we'll convert it to integer. So let's first look at the values. So here we see we have decimal points. So if I run this now and I check, take a look at this, and now we can see that the decimal value has been removed. Okay. And similarly, we have this age column. Age column we have here. We can simply change it to float. And there we see it is now in float 32 format. So now it all has a decimal point. So this is typecasting. The next thing that we have is duplicates. Duplicates are repetition of data. They don't add anything useful in our data set. We are just doing some sort of replication. All right. So this can lead to bias towards specific answers because they have been repeated multiple times. So let's see. So we'll load our data set again. We'll take a look at the values. So here, wherever it is saying false, that row number does not have any duplicates. Wherever it is saying true, at that point, we have duplicates. So based off of this, we can say that row number 17, row number 23, and row number 27 have duplicates. All right. So let's check. Let's look at the sum. We have 3 duplicates. So here we can see the size of the data frame. It is 32 rows by 11 columns. But out of those 32 rows, 3 are duplicates. So we'll take this. And now we remove the data and we can see that those 3 duplicate values have been removed. All right. The next thing we'll do is we'll take a look at something called outliers. Now, outlier treatment is very important. We use outlier to detect anomalies in the data. So these anomalies means these values don't fall within the rest of the distribution of that data. All right. So to detect outliers, we use something called box plot. Box plot is a univariate diagram, univariate graph. That means it is only taking one variable and it is plotting for that. So this again goes, like I said, that EDA and pre-processing go hand in hand and they form the backbone of any machine learning algorithm. All right, so let's see. So we'll import the necessary libraries. We take a look at the data. Now you have to remember one thing, box plot can only be performed on numerical data. You cannot do box plot for object data. Okay, so wherever you have numerical points, we use box plot. Okay. Done. All right. So let's see. So let me open up the visualizations. All right, here we go. Now let's look at this visualization. So this is our quantile values. This is Q1 and this is Q3. This is the median of the data and this is Q2. This black line is the median of the data. So first thing we do here is we calculate our IQR. IQR is given as Q3 minus Q1. So we take the Q3 value and the Q1 value and we subtract it. Now, if we look at over here, these two values would fall somewhere here. So let's say, for example, our Q3 value is 50,000 and our Q1 value is, let's say, 22,000. So our IQR would come out to be nearly 28,000. All right. So now we have done the first part of our calculations. The next thing we'll do is we'll calculate the fences. These fences define the boundary of our outliers, where whatever values fall within these fences, they are known as not outliers. Whatever fall outside these fences, they are known as outliers. So we have left fence and we have right fence. So this is our left fence. How is it calculated? Okay, left fence. How is it calculated? We take Q1 minus 1.5 times the IQR. Okay. So what is Q1? 22,000 minus 1.5 times 28,000. This comes out to nearly minus 20,000. So in terms of salary, minus 20,000 doesn't make any sense. So we are stopping at 0. Okay. Similarly, we have this is our right fence. This is calculated using Q3 plus 1.5 times of IQR. So we take 50,000 plus 1.5 times of 28,000. This comes out to nearly 92,000. So our right fence boundary limit is 92,000. So what we are saying here is any value that falls between 0 and 92,000, it is considered as not outliers. Anything that falls outside of these boundaries is known as outliers. So we have a few points here that lie beyond the right fence. So these values are called as outliers. So moving forward, we can also check for outliers in age. And here we can see that we don't have any such outliers. All right. So next thing, we'll calculate our IQR values. So we'll calculate the upper limit and the lower limit. Those values are calculated quite near to the estimated values that we were taking. Now, let's draw this box plot again. We have two ways of treating outliers. The first way is simply by deleting them. This is known as trimming. So what happens in trimming? In trimming, it will take these data points and it will simply delete them. Okay. So this is what trimming does. The second way of doing it is Winsorization. In Winsorization, we are moving the points from the outliers to an acceptable range. Okay, so we are taking these data points and we are moving them inside the fence by changing their values. All right, so this is known as Winsorization. So first we'll remove the outliers. So here we see the data frame is of the size 310. So this shows where are the outliers. So here we have one outlier, second outlier, third outlier, fourth outlier, and that's it. Okay, so now what we'll do is we'll remove these outliers, and here we can compare the shape. So we had 4 outliers and those 4 values have been removed. Okay, now we can draw the box plot again and we'll see that our outliers have disappeared. Okay. The second thing we do is Winsorization. We'll replace the outliers by the maximum and the minimum limit. So we'll take this upper value and what we'll do is we'll change the outlier values to these upper limit value. So let's import the library and let's run it. We'll fit transform our data and then we can take a look at the box plot again. And again, we have removed the outliers. Okay. The next thing we have is zero variance or near zero variance features. Let's say we have a country column and we have 10,000 observations. All right. And all of the observations are saying as India. Let's say we have 9,999 are India and America is 1. Okay. So this is where our outliers, this is what we call as a zero variance or a near zero variance feature. We don't use these columns because they don't add anything useful to our machine learning algorithms. Okay, so we'll simply check if they have any near zero variance. No, false, 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 and again false. Okay, then we do missing value imputation. So let me go back here. Missing value. In missing value, in Python, missing values are represented by NaN. Okay. So let's take it. Let's see what we do in missing value. So we do something called imputation. Imputation is replacing the missing value with appropriate value, or we can simply remove them. Sometimes we just simply remove the missing values. So let's do imputation. Imputation is of 3 kinds. We have mean, we have median, and we have mode. Now we all know how to calculate mean, median, and mode, right? Mean is the average value. So what we do in mean imputation is we replace NaN values with the mean. All right, we take the mean of the data and we replace our NaN values with that. In median, we are looking at the middlemost value. So here what do? We replace NaN with median. So quite simple concept to understand. You just find the mean, you replace the average NaN values with mean, or median, you replace the NaN values with median. The problem with this is this gets affected by outliers. All right, this gets affected by outliers. So sometimes we prefer using mean over median. All right. The second thing we have mode. Third thing we have mode is we use it the most common value. So we replace NaN values with mode. Okay. Now, one more important distinction. This can only be used in numeric. Only numeric. This can be used in both numeric and categorical. All right. So this is imputation. Now let's look at how imputation is performed. So first we'll check for missing values. Looks like let me just find the data set. Just give me a second. All right, so let's load the data set. We'll check for missing values and we can see that we do have a lot of missing values. So here we can simply use, here we'll use mean to impute, and here we'll use median to impute. So again, we can check that missing values are gone in these two columns. Similarly, we can use mode, and now that is also gone 0. Then we have discretization. In discretization, we are converting our continuous data into some discrete data. Okay, so let's say, for example, let me load up the data set. Which one we are using? Ethnic diversity. So we'll load the data set. Which one? What is it called? Data. So here we have salaries. So salaries is continuous. So what we'll do is we'll create bins and we'll convert it to some other values. We'll use binning technique here. So we'll be converting it into high and low salary using the mean as the middle point. So if we look at it now, we have high, low salaries. So we'll calculate the values. So, and this is our discretized values. Then we have dummy variable creation. In dummy variable creation, what we do is we replace the categorical values with some sort of dummy variables. So let me restart the console here. All right. So we'll load our libraries and we'll load our data set. So dummy variables, like for example, we have account, position, state, sex, marital status, citizen description, employment status. These are all categorical values. What we'll do is we'll convert them into some sort of numerical values. All right, we'll drop the unnecessary columns and then we'll convert all of it into dummy variables. So here you can see that it has been converted into numerical values, zeros and ones. Similarly, we can do one-hot encoding. We'll apply one-hot encoding. And here again, the values are converted into zeros and ones. Or we can do label encoding. So here if we look at sex now, it has been converted into zeros, ones and other values, males and females to zeros and ones. Same thing we can do for marital description and citizen description. So again, it has been converted into numerical values. And then finally, we have standardization. In standardization, we try to reduce the range of our data. So what data are we using here? Empty cars. All right. So here we'll use the standard scaler. So in standardization, we have two methods. We can either use the min-max scalar, where we are taking x of I, that means any value of x minus the minimum value of I divided by maximum minus the minimum for each value of I, and we are doing summation here. Okay, so this is the min-max scaling. This will reduce the range of the numbers to between 0 and 1. Okay, so let's load that. So first we'll do min-max scaling. Okay, so we apply this. Ethnic diversity. Okay. So we look at the description of the data, we get the dummy variables, and then we'll create the min-max scaling. So here if we look at B, this contains a minimized, maximized values. All right. And then finally, we do standardization. In standardization, we take any value of X, we subtract it from its mean, and we divide it divided by the standard deviation. What happens in this is mean becomes 0 and standard deviation becomes 1. Okay. So we'll run this. Let me just load the data set again. We'll run this, we'll import our standard scalar. We'll apply it on a data frame, and then we can print the res. So here we can see that the mean is near 0 and the standard deviation is nearly 1. Okay, so these are the various pre-processing techniques that we use. All right. So with this, we come to an end for today's session, and then we'll continue tomorrow. Thank you everyone for joining.